So we've spent some time with arithmetic sequences, but does every pattern increase by a constant value? I think not. If you look at the numbers that I have here, you should see a different type of pattern. And I'm curious, what do you see? What do you see when you see numbers like 3, 9, 27, and 81? Yeah, what do you see? Yeah, Billy, exponents? Yeah, I see exponents. You mean like 3 to the first power or like 3 to the second power? Yeah, 3 to the third power? Sure, this is like an exponent pattern. How about the other group of numbers here, the other sequence? 2, 1, a half, a fourth. What do you see? How would you explain the pattern? Yeah, Susie. Multiplying? You mean like multiplying by a half? Yeah, if you multiply 2 by a half, you get 1. If you multiply 1 by a half, you get a half. So yeah, it looks like we could say that we're multiplying. But if you felt like that both of these incorporated exponents and both of these incorporated multiplying, well, you also would be right, because certainly this one at the top could be argued to be multiplying by 3, and this one at the bottom could be argued to be 1/2 to an exponent. Now you'd have to be a little careful because this would actually be 1/2 to the -1 power, right? And then we'd have 1/2 to the 0 power, and then 1/2 to the first power. And we could describe it with exponents, because the truth is that exponents and multiplying are in the same family. They're in the geometric family. You see, when numbers are increasing, or I should say changing, by a product of the preceding term and a common ratio r, we would say that we have a geometric sequence. Now, that's fancy talk for what I showed you on the other page, where basically we can multiply by a number, or we can describe it with exponents, because they're the same. Let's dig a little deeper into what it means to be geometric. What if I asked you for the next two terms, and I gave you 8.9, 50.73, and 289.161? What would you do to find the next two terms? I want you to think on this one. If we were in the classroom, you would be doing something right now, so you should be doing it while you're watching the video. Are you pulling out your calculator? Are you doing something with your calculator? Be careful. This would be a good point in the video to pause and just see if you're able to figure out what's necessary to get the next term, the next two terms. You're dividing, aren't you? You're dividing, but which way are you dividing? Okay, did you take 50 divided by 8.9? Well, if you did, then you'd be finding what's known as the common ratio. Now that common ratio comes out to be 5.7. And if you test it with the next set of numbers, that is, if you test it with 289 divided by 50, you'll discover why we call it a common ratio, because it also comes out to be 5.7. The common ratio is a big part of a geometric sequence, because obviously if you know it, you can multiply it to get the next number, and the next, and the next after that, which I don't have too much space here, but if you multiply by 5.7, which is pretty easy to do, you can get 1,648 and a bunch of decimals. I'm going to leave out the next term. We'll just multiply again. But the point behind this is that we come up with a little statement about this common ratio. And the statement is that the common ratio, that is r, is always going to equal the nth term divided by the term before the nth term. And we would call that n minus 1. Now, I want you to get familiar with this notation. When you see a sub n, that just means a term in the sequence. It could be the last term, it could be just any term in there. But when I say a sub n divided by a sub n minus 1, I'm basically taking a term and I'm dividing it by the term before that term. I'm dividing it by the term before. So you have to always divide in the right order, and that'll get you that common ratio. Let's investigate a little more about geometric sequences. Would this be a geometric sequence? Are you dividing? Once again, because, well, a geometric sequence always involves that common ratio. 151.2 divided by 63? 2.4, right? 378 divided by 151.2? 2.5. And then when you do the next one, it's 2.6. Do we have a common ratio? Well, no, we don't. Do we have some type of pattern here? Sure, but it's not geometric. All right, now I know you could tell me what the next term is. You're just going to multiply by 2.7, but it's not a common ratio. So therefore, it doesn't fit into the geometric pattern. So what really is the geometric pattern? In other words, what formula can describe for us a term in something that's geometric? Let's create the formula. Now here's a real simple geometric pattern, 2, 6, 18, 54. Okay, notice that I'm describing it using the notation a sub 1, a sub 2. That just means the first term, the second term. As you look at these numbers, you should very quickly be coming up with the common ratio of 3. But what I want to see is you can describe these numbers as how they relate to the first term. Now, how does 2 relate to the first term? It's the first term. It's a sub 1. How does 6 relate to the first term? Well, it's the first term times that common ratio. How about the third term? How does it relate to the first term? Well, it's the first term times how many common ratios? Times another one, right? Times 2 common ratios, otherwise known as 3 squared. Are you catching on? The fourth term would be the first term times how many common ratios? Well, times 3. We're starting to create a pattern. Do you see it? Let's make it a little bit more generic, because the common ratio can be described as R. So everywhere where I have the number 3, I can put the letter R in here to help us see how to write a formula for the nth term. Do you think you can do it? It's always going to be the first term times how many common ratios? How many? Have you noticed? If you have the fourth term, you need 3 common ratios. If you have the third term, you need 2 common ratios. So what if I have the nth term? How many common ratios do I need? That's right, n minus 1. So we have a sub 1 times r to the n minus 1. What is that? That's a formula for the nth term of a geometric sequence. And that makes up our first geometric formula. A sub n equals the first term, which is a sub 1 times r, the common ratio, to the n minus 1 power. There's also another version of this. We call it recursive. Sometimes this can start to get a little bit kind of a little new for students, but recursive just means that the only way that I'm going to know the next term is to know the term before it. And that's all this formula really says. It says that the next term, we'll call it a sub n, the next term is going to be the term before it, a sub n minus 1, times another common ratio. If you really think about what's said here, it's not much of a formula. It just says to get the next term, I need the term before it times r. But that's a recursive formula, again, because I need to know each term along the sequence in order to get the next term. Let's do some math problems. Let's find the 14th term of this sequence. 1, negative 1/3, 1/9, negative 1/27. Now, certainly, I'm not expecting you to multiply numbers together 10 more times. That's not the idea. The idea is to use the formula. And as you get to that formula, you find out very quickly that the first thing that we need is the common ratio. That's right, the common ratio is always found by dividing. Now, if you do a little bit of dividing where you take like the nth term, maybe negative 1/3, and you divide it by the term before it, maybe 1, then we seem to come up with what appears to be negative 1/3. If you do a little bit of thinking, negative 1/3 is how I can get to the next term, and the next. So I feel pretty certain that we have the common ratio. So that means I can find the 14th term. We'll call it a sub 14. And when I plug into the formula, I just need the first term. The first term is 1. I need the common ratio. Okay, we found that to be negative 1/3. And then I need an exponent. Now the exponent's going to be n minus 14. Check that. It's going to be 14 minus 1. N equals 14. And so we end up with, of course, an exponent of 13. We actually end up with negative 1/3 to the 13th power. Now, before you put that in your calculator, let's think a little bit about what happens if I take negative 1/3 to the 13th power. First of all, it's going to be an odd number of negative numbers, right? So it's going to come out negative. Second of all, it's going to be a large denominator, like 3 to the 13th power. Well, again, if you put that in your calculator, you're just going to get like some messy scientific notation. So instead, it's a little bit more formal for kids to write an answer. Let me see where I want to put this. To write an answer like that by just describing the value of the denominator. 3 to the 13th power, or 1,594,323. Okay. Again, you may give the answer in an exponent form, or you can actually multiply it out. But I don't want to see the scientific notation. I don't want you to, on your calculator, just take negative 1/3 to the 13th power. You're just going to get a very small scientific number. All right, well, that was interesting. How about something like this? What if we want to find two geometric means? Now, if you're saying geometric means, did I miss something? Well, that's kind of some terminology that basically refers to the numbers in between the numbers of a geometric pattern. Okay? The numbers in between the numbers in a geometric pattern. 136, some number, and 459. Boy, I wish I knew that common ratio. I bet you do too. That's exactly what you need to find. Now, you can find that common ratio with brute force. Brute force would take 459 and divide it by 136. But do you realize that that's the ratio that's between three sets of numbers? So what are you going to do with that? Are you going to divide it by 3 some more? Well, the problem with brute force is that it sometimes leaves out the mathematics. But let's do the mathematics. In other words, let's do the formula. The formula says a sub n, which I want you to realize that we can use 459 as a sub 4. And then we need a sub 1. So I don't see why we can't use the first number as a sub 1. They're same thing. And I'm kind of getting to a point here where I can start plugging some numbers in, right, to my formula. So a sub n, which is a sub 4, is equal to the first term, 136. Oh, good, my common ratio. That's like what I'm trying to find. And then, I can actually, find the exponent. I can find it to be 4 minus 1 because n equals 4. So I've kind of quickly created for myself a little formula, a little equation. And as I always say, what do you do with little equations? Well, you solve them. Now, it turns out that the first thing you're going to do is divide by 136. That's convenient because that was kind of what we were going to do with brute force anyway, wasn't it? So if we divide by 136, we end up getting, 3,375. And, okay, that equals r cubed. Ooh, I got to get rid of the cube. Yeah, so you're not going to divide by 3. You're going to use more of an opposite type exponent. Now listen, there's 2 ways to do an opposite type exponent. You can raise both sides to the 1/3 power. If I raise both sides to the 1/3 power, I can do that on my calculator. Make sure that you carefully do 1/3. You can also do the cube root. Of course, you'd have to locate the cube root function. It might be in your math menu. But either way, make sure that you can do that. I'll be honest, I prefer raising both sides to the 1/3 power because, of course, I'll be able to do that with any exponent. Make sure you can do it. You should be getting 3/2 or 1.5. Of course, that's your R value, right? R equals 3/2. Our common ratio. And once you have a common ratio, all you got to do is multiply. So yeah, just multiply 136 by 3/2. That's pretty easy. That'll get you your next number in the sequence, 204. And multiply it one more time and you get 306. The formula, that's where it's at because the formula has the math built into it. All right. Now, what if we want to turn this sequence, or excuse me, what if we want to take this sequence and add the numbers together? What happens when you add numbers together in a sequence? Do you remember from the last lesson? Yeah, it comes out to be what's known as a series. Okay, and of course you actually end up with a number for this. It comes out to be 1,105. But more importantly, we want to understand that now I have what's known as a geometric series. And again, a geometric series would just be the sum of geometric numbers. I wonder if there's a formula for a geometric series. Well, there is, but it's a little complicated to create. So just kind of for simplicity's sake here, I'm going to show you the formula. Is that all right with you? It's this. It's S sub n equals a sub 1 minus a sub 1 times r to the n all over 1 minus r. It's a rather interesting formula, actually, because if you kind of look it over, it really just boils down to a couple things. It actually, interestingly, boils down to the first term. As you can see, you use the first term twice. It boils down to the common ratio. That's probably not a big surprise. And once again, that's used twice. And then we need to know the total number of terms that we're adding together. We call that n. Geometric series formula. All right. This is what you can use if you want to add up a bunch of geometric numbers. You know, like more than just like a couple geometric numbers. Like maybe if we want to add eight geometric numbers. Okay, now we're going to find the 8th partial sum. Again, that's just kind of fancy talk for adding 8 geometric numbers. Okay, so we've got 3 minus 6. Who put that minus sign in there? Plus 12 minus ... Okay, now I wouldn't be surprised if you could figure out the remaining 5 numbers and just put them in your calculator. And some of you that are into maybe like a race, you can try to race me and see if you can do that faster. But if we're going to use the formula, then we need to understand that we need, once again, the common ratio. Okay, now that common ratio is always found by dividing a term by the term before it. You know, like 3 or -6 divided by 3. And we can always double check to make sure that the next is going to work the same. And it will. So it looks like -2. By the way, the common ratio can be negative. -2 is going to work. So if I want to find the sum, the 8th partial sum, we could call that S sub 8. That would stand for series, or the 8th series. I'm sorry, the series of 8 numbers is really what that stands for, the series of 8 numbers. I just need the first term. Looks like that first term is 3. And then we're going to subtract the first term. And then we're going to multiply that by the common ratio to the nth power. Now, the nth power is just going to be the total, or the n, the value for n is just going to be the total number of numbers. And then we get this little 1 minus r going on down here, 1 minus negative 2. Okay. We got a lot going on here. We got negative numbers. We got the order of operations. We should be careful about this. Make sure that you can put it in your calculator. I like to do the exponents first so that students can see that you end up with positive 256. Also like to do the parentheses in the denominator so students can see that you end up with the number 3. Kind of interesting here because you could cancel the 3's if you want to, or you could just kind of do the math and find out that the numerator is 765, and when you divide that by 3, you end up with negative 255. Interesting, if I would have listed out the remaining 5 numbers, they apparently would have started to get pretty big, or maybe I should say pretty small, because we're going to end up with a negative value. In other words, our final answer being a sum of negative 255. Geometric sequence. Numbers that change by a common ratio, which implies multiplying and exponents. So we arrive at the exit problem. Yeah, I'm going to ask you to do an exit problem here, kind of put you to the test right away and see if you can find a 6 partial sum. And notice that I'm being a little tricky here. I'm only giving you the 3rd term and the 5th term. Okay. So, what do you need? Well, it's kind of been the answer for the day, hasn't it? You need the common ratio. How are you going to get that common ratio? I hope you don't use brute force. Brute force would take these numbers and try to divide them and maybe hope for the best. But it looks like that we got a little lottery ticket here. You know, maybe we'll get lucky and win the lottery. Maybe we can scratch this off and see what hints we have. Hint number 1. Hint number 1. It's going to help you to get the common ratio. Okay, to get that common ratio, what you're going to do is a little temporary thinking. You're going to temporarily think of this problem as a geometric mean. I'm talking about one of these situations where you can think of 16 over 3 as the first term, and then 64 over 27 as the third term. You see, what this does is this allows you to plug into our original formula. And when you plug these numbers into the original formula, you'll be able to solve for r. Okay, you'll be able to solve for r. Now, once you get r, then you're going to need, this is a pretty nice hint, you're going to need the real first term. You're going to need the real a sub 1. All right, so how are you going to go backwards and get the real a sub 1? Well, this time you're going to plug in the real a sub 3 back into that original formula. The only time you have to use our series formula is when you're ready to set up that final answer, when you're ready to find that 6 partial sum. Okay, it's going to take a couple steps. Work it out. The exit ticket is actually on Google Classroom as a form. So I'd like to see you solve it there and then, of course, submit your answer. All right. Geometric sequence, geometric series. We'll see you next time.